Welcome. Today we're going to pull back the curtain on one of the most powerful and, let's be honest, sometimes intimidating features in C++, templates. If you've ever wanted to write code that's more flexible, reusable, and super efficient, then you are in exactly the right place.
Okay, so to really get why templates are such a game changer, let's start by looking at a problem. A really common, kind of frustrating problem that I guarantee every C++ programmer has run into.
So take a look at this. On the left, you've got a max function that works for integers. And on the right, well, it's the exact same logic, but this one's for doubles. See the issue? Because C++ is so strict about its types, we're literally forced to copy and paste our code just to handle a different kind of number. It works for sure, but it doesn't feel very elegant, does it? And that really is the million-dollar question. It's just not efficient, and it becomes a real pain to maintain. Imagine you find a bug, or think of a better way to write it. Now you have to remember to change it in 2, 3, maybe 10 different places. So the real question is, how do we write this logic just once and have it work for basically any type we throw at it? Well, the solution is a core C++ feature that acts like a blueprint for code. Instead of us writing every single version by hand, we just give the compiler a master plan. Then it automatically builds the specific versions we need. This whole idea is called generic programming, and the principle behind it is simple but really profound. Instead of writing code tied to a specific type like int, we write it for a generic placeholder type. We're defining the pattern, not every single specific implementation.
And this quote just nails it. This is the goal. This is the dream, right? To capture the logic of an algorithm one time, and then let the compiler do all the boring, repetitive work of applying it to whatever types we need. So how does this whole blueprint thing actually work? Well, the magic happens at compile time, which is key. First, you write your generic template. Then the compiler scans your code and sees you using it with, say, integers. At that moment, it generates a brand new, fully specialized version just for integers and slots it right into your code. It's like having a little robot that writes code for you. And what's the runtime performance cost for all this amazing flexibility? Absolutely zero. Zilch. Nothing. This is the crucial takeaway. Because all of this code is generated before your program even runs, there is no performance hit. You get this powerful, reusable code that runs just as fast as if you'd written every single version by hand. Okay, so let's dig a little deeper. There are two main ways you'll see templates used, for functions and for classes. They serve slightly different, but equally important jobs. This chart breaks it down perfectly. Template functions are for generic actions or algorithms. Think max or sort. They're like a reusable tool, like a magical wrench that can fit any size bolt. On the other hand, template classes are for generic containers, things that hold data. Think of std vector or std map. They're like a customizable box that you can build to hold anything you want. Now, why does all this matter so much? Well, here's the fun part. If you've been writing any modern C++, you have already been using templates all over the place, whether you realized it or not. That's right, the standard template library, the STL, the absolute bedrock of modern C++. It gets its name and all of its power directly from this feature. It's not just a clever name. I mean, just think about it for a second. std vector. It can hold integers, strings, or even your own custom objects. std sort can sort a collection of pretty much anything, as long as it can be compared. This incredible flexibility is only possible because they are all built as templates. So let's bring it all home. We can boil down the incredible benefits of templates into 3 essential takeaways. First, performance. I know we've hit this point a few times, but it's that important. You do not pay a speed penalty for using this amazing abstraction. The compiler does all the heavy lifting up front, so your final program is as fast as it gets. Second, reusability. And this one is huge. You get to stop that tedious, error-prone cycle of copy-pasting code. Your code becomes cleaner, it becomes shorter, and it's way, way easier to maintain. And finally, type safety. Unlike some older tricks like C-style macros that just do blind text replacement, templates are a core part of the C++ type system. This means the compiler checks everything for you, catching errors early and saving you from those really nasty, hard-to-find runtime bugs. At the end of the day, that's the real magic here. Templates shift how you think. You stop writing one-off solutions and you start designing powerful, flexible, universal components.
It's a foundational tool for building seriously robust software. So the only question left is, what are you going to build with them?